This is Introduction to VLSI Design, and this time we will talk about the power. So in this talk, we will talk about the power and energy, and then we will focus on the two main types of power, which is the dynamic power and the static power. So starting with the relation between power and energy, power is drawn from a voltage source attached to the VDD pins of a certain chip. The instantaneous power is power as a function of time will equal to the current and the voltage, and both of them as a function of time. The energy will be the integration for a certain period of time from 0 to t of the power. Now, the average power is actually equal to energy over time, which will in turn equal to 1 over time of this period from 0 to t, from time 0 to time t of the power consumption. That will be the average power. Now, the power consumption components, we have two main components, the dynamic power, which is this one, and the static power. So reducing the power consumption in chips is a major design goal. It's in everywhere, actually. For example, in portable devices, in handheld computers, mobiles, and you always worry about the power consumption because of the problem of overheating. If the chip is overheated, it won't perform well. It will increase its age until you end up with an error or a complete failure of the chip. The power is consumed due to the current flowing from the supply to the ground. So if you want to reduce the number, reduce this current flow. Now, the power and timing are interrelated. Usually, if you are if your target is a faster logic, this means that you will consume more power. The power consumed in the CMOS gates actually what we will call the total power is equal to the dynamic power plus the static power, which is the main two components. The first one, dynamic power, is composed of two types, the switching power and the short circuit power. And this is actually because of charging and discharging of transistor capacitance, which will be this is the switching power. And we also have the short circuit power, and we will talk about each one of them by itself. Now, the static power, we have four components: the subthreshold power, or the power consumed because of the subthreshold current. Also, the other one is because of the gate current. The third one is because of the junction current. And the last one is because of the contention current. We will focus on the subthreshold current and the gate current. For the junction, the contention will be negligible. Now, the static power is generated because of the leakage. The leakage is actually the main reason for having a static power consumption. So the leakage current that comes actually in many forms, like from the subthreshold leakage, junction leakage, gate leakage, and the contention leakage or the contention current. And the two main forms that we will focus on is the subthreshold leakage and the gate leakage. The subthreshold leakage and the gate leakage. The dynamic power, now we will start by talking about the first type, which is the dynamic power. We will spend some time on it. And then once we are done, we will move to the static power. So the dynamic power, it's because of this switching power that occurs when charging and discharging of the transistor capacitance. So for example, if you have a capacitance at the load of a certain gate or certain CMOS design, so at this output node, you have this capacitance. Either you want to charge it or discharge it. If the pull-up network is working, then you are charging this capacitance. If the pull-down is working, then you are discharging this capacitance. According to this simple mathematical calculation, the switching power will be equal to 1 over T of a certain period of time from 0 to T of the current multiplied by the voltage. And this is what we said about the instantaneous power. Now, we know that the VDD at the VDD node here is constant, so we can take it out from the integration. And now this integration from time 0 to T of the current is actually affected by the window of time, which is T, the amount of current that you are having based on the capacitance, the amount of capacitance. The more capacitance that you have, the more current that you need. So the capacitance is there. Also, the frequency at which you are charging and discharging, how frequent you are doing this. And this is called the FSW, or the frequency of switching, and the voltage at the source, which is the VDD. So now we have another VDD. The first VDD comes from the fact that the power is actually the current times the voltage, and we take it out. And there's the other VDD because of it's the main factor, or one of the main factor, the major factors of charging this capacitance when you have a certain current. So from this calculation, we know that we can get the VDD outside too. So we have C multiplied by the switching of the frequency of the switching multiplied by the voltage squared. Now the T can go out with the T because you have it in numerator and denominator, so cross them out. So that's the end result. So the dynamic power is now, or the power, or the switching power, which is going to be the dynamic power, is equal to, or mainly affected by the capacitance, the voltage, and the switching frequency. Now, for any gate, the switching frequency won't be like constant. Sometimes the switching is fast, sometimes it's slow, based on the circuit itself, based on its input. So we will have what we will call the activity factor. So suppose the system clock frequency is equal to F. Now the switching power is actually will be equal to alpha. We will introduce this term, alpha times F, which is the system clock frequency, where this alpha is actually the activity factor. If the signal is a clock, meaning alpha will be equal to 1. So you are switching with full capacity. Alpha is 1, so the frequency of the switching will be exactly the frequency of the system clock. If the signal switch once only per cycle, so now alpha is equal to half. So the frequency of the switching will be 50% of the system clock frequency. Now the dynamic power equation, or the switching power equation, is equal to alpha CV squared times F, where F is the system clock frequency. And now we need to find alpha whenever we have a specific gate. But before we do this, let's talk about the second type of the dynamic power, which is the short circuit power, or based on the short circuit current. Now, a small percentage of the dynamic power is short circuit power. When transistor switches, both the NMOS and the PMOS network may be in a brief moment of time, momentarily on at once at the same time. At this time, you will have a connection between the VDD and the ground. But it's not for a long period of time, otherwise we will burn the circuit. It's for only a fraction of the nanosecond. So considered to be less than 10% if the rise and fall times are compared for input and output. This will lead to short circuit current, and we will generally ignore this component because it happens in a very low or a very brief moment of time with a low also probability. Now, let's have an example. At this point, the dynamic power consumption is the same as the switching power consumption because we ignored the short circuit power. So in this example, we have a design with 1 billion transistors composed of certain logic with 50 million transistors, and the remaining 950 million is for memory. So from this 1 billion transistor, 95% of it is memory and only 5% is logic. Now the 50 million logic transistor, the average width is 12 lambda and the activity factor is 0.1. Now for the memory transistors, the average width is 4 lambda, which is much smaller, and the activity factor is also very low, which is 0.02. And there is a reason for it, because when you are writing any program, when you convert it to assembly language, the load and the store, the one that accesses the memory, these instructions have a low percentage compared to other instructions. Also, we have 1 volt VDD with 50 nanometer processes. The process of the generation that we are using actually is 65 nanometer process, but for so many reasons, we will consider 50 nanometer in calculation. Now, the capacitance we have is 1 femtofarad per micrometer for a gate, and for a diffusion is 0.8 femtofarad per micrometer. And you were asked to estimate the dynamic power, given that the system clock frequency is 1 gigahertz, and you were also told that to neglect the wire capacitance and the short circuit current. So, to solve this, we recall that lambda is equal to the feature size in micrometer divided by 2. And in calculation, we will use the 50 nanometer, which is a 0.05 micrometer divided by 2. So 1 lambda will equal to 0.025 micrometer for every lambda. And this is the breakdown that we just mentioned. So to get this, we know that the power consumption is actually, or the switching power consumption, dynamic power consumption is alpha C VDD square times F. We have the frequency, 1 gigahertz. We have also the voltage, the VDD, which is 1 volt. The capacitance were given to us, not in terms of farad, it's in terms of farad per micrometer. So we must know how many micrometers we have in the whole design, so we can get the capacitance. Similarly, we have the activity factors broken down into both types. On top of all of this, the width were not given to us in terms of micrometer, it was given to us in lambda. And this is why we need to use this conversion. Now we will calculate the C logic and the C memory in terms of farad. The way to do this, we will say how many logics we have. We have 50 million. Each one of them is 12 lambda, which is multiplied by 0.025 micrometer per lambda. So the lambda will go away. And now you convert to micrometer. And now we multiply this by the addition of both capacitance, which is the 1 femtofarad plus the 0.8 femtofarad per micrometer. And now also the micrometer will go away with this micrometer, and you will end up with only farad. The total is 27 nanofarad if you do this calculation. For the memory, we'll just replace the count, the correct count, and also the correct size to get the capacitance of the memory. Now the dynamic power is, as we mentioned, it's alpha CV squared times F. Alpha is 0.1 for the, it's 0.1 for the logic, and it's 0.02 for the memory. So we will multiply 0.1 by the capacitance of the logic times V squared times the frequency plus the memory. Now it's the memory term. So it's 0.02, which is the alpha, the activity factor of the memory, times its capacitance, which is 171 nanofarad times again the VDD squared times the frequency, which will end up with 6.1 watt. This is for the dynamic power, and this is reasonable because this is actually an old process. In recent processes, the power consumption is getting so high that it's more than 100 watt. Now, the dynamic power reduction, we need to reduce the power consumption for the switching, the dynamic power consumption or the dynamic or the switching power consumption. We do this by reducing all these four factors. We reduce the activity factor by reducing the switching activity, removing glitches, removing unnecessary switching. This way you don't have switching from 0 to 1 and 1 to 0. So the activity factor will be lower. We reduce the capacitance by reducing the capacitance, the capacitive load. We reduce the gate capacitance by having fewer gates of the logic or small gate sizes. Reduce the wire capacitance by having good floor planning for close communication. If you have two subsystems, make them close to each other. You drive long wires with inverters or buffers rather than complex gates which will have more wire capacitance. Also, we reduce the supply voltage, and this happens in every generation. The newest or as new generation comes, the voltage or the VDD, it should be reduced. But unfortunately, at this time, we are kind of reaching a wall where we cannot reduce the voltage anymore. And we also reduce the frequency of the non-critical paths. This way, the frequency is kind of reduced and the power will be reduced. We can't reduce the frequency at the critical path because it will directly affect the performance. Now, for the activity factor estimation, you have a certain gate and you need to find alpha. How to find alpha? To do this, let's assume that P of I is actually the probability that node I is equal to 1. So we have P of I. We can have P of I bar, which is actually 1 minus P of I. Remember, this is probability. So it's going to be between 0 and 1. 0 means that this event is impossible to happen. 1 means that this event will happen 100%. So it's between 0 and 1. If you want to calculate alpha, it's actually the probability of I times the probability of I bar. To understand this better, the activity factor is actually happening if you have this event. When you have 0 followed by 1. This is a switching. Or it could be 1 followed by 0. Now you have a switch. So for this event to happen, you must have a 0 and then you have a 1. Or let's have this case. You must have 1 followed by 0. So you must have this event happening, the event that this node becomes 1, which is given by the probability P of I. So we have P of I here. And I'm emphasizing this, we have an and, so we multiply the probability of having a 0 after that, which is going to be the opposite of this probability, meaning that the node is equal to 0, which is P of I bar. So it's time P of I bar. And this is what we mean. And this way we get the activity factor at that node I. So at the beginning, it's completely, at the beginning, when you have inputs, it should be completely random data. So you have the P equals to 0.5 and P bar in turns will be 0.5, meaning that this node will be 1 50% of the time, and it will be 0 50% of the time. Now the activity factor will be the 0.5 times 0.5, which is going to be 0.25 or a quarter or 25%. So the data is often not completely random. For example, this is if we assume random data, but know that some data are not completely random. Example, the upper bits of a 64-bit word representing a bank account balances. They are usually zero because we don't have so many billionaires or millionaires in the world. So the data propagating through the ANDs and the ORs has lower activity factor. It's actually depending on the design, but typically the activity factor is around 0.1. So let's calculate the activity factor for different gates. To do that, or to calculate the activity factor, we need to calculate the probability first. So we will get the switching probability, and from the switching probability, we can calculate the activity factor. So let's figure out what's the switching probability for these circuits. For a 2-input AND, for a 2-input OR, for a 2-input NAND, for a 2-input NOR, and for a 2-input XOR. Actually, you can do this many ways. One of the easiest way by knowing the truth table. The truth table of the AND is like this, and you can see that you have 25% of the time for combination. So it's going to be a quarter. And to calculate this, we do it in mathematical form by having the probability of A being 1 times the probability of B being 1. So you look at the ones. And this is what we have, the probability of A times the probability of B. For the OR, we have ones in three positions. So it's going to be 3/4 or 75%. That will be the probability. To get it in mathematical form is actually, instead of getting this and then you add it to the second and then you add it to the third situations or the third combination where you will have 3 terms like this, the first term plus the second term plus the third term. Instead of doing this, we know that this is 0. So the 0 happens when you have the probability of A being 0, meaning that the PA bar times PB bar. This will give us the probability of the PY bar. So to get, if that's the PY bar, which is the PA bar times PB bar, then to get the PY is going to be 1 minus that probability. So it's 1 minus that probability. So sometimes it's good if you have only fewer number of zeros, it's good to get this one and then say that the probability is 1 minus this situation. So for a NAND, the 2-input NAND, this is the truth table for it. Again, we are facing the same thing. So we look at the 0 and we say that it's 1 minus that probability, which will happen in probability of A times the probability of B, because we have 1 NAND. For the 2-input NOR, we have the probability of P, or the probability of A bar times the probability of B bar, which is this one. And for the XOR, 2 inputs, we have 2 ones and 2 zeros. So we will just focus on the ones, which will be the probability of A bar times P, the probability or the probability of A bar times the probability of B, which is this one, plus the probability of A times the probability of B bar, which is this. That's the way to do it using truth table. Now we got these results for 2 input circuits, some examples of 2 input primitive gates. Let's try to extend this to 3 inputs to understand that we can extend it actually to more number of inputs. So for AND, after 2 inputs, and the OR and the NAND and the NOR, we just got this in the previous slide. To extend it to 3 inputs, you can see that we are actually multiplying by the probability of C. Here we say 1 minus, and then you have the probability of C bar. Here it's 1 minus, and you are adding actually the probability of C. And here we have actually the probability of A bar times the probability of B bar. You have a two input NOR. For a three input NOR, it would be the probability of A bar times the probability of B bar times the probability of C bar. Now, how to calculate this if you have a certain circuit? How to calculate it? So at the beginning, the inputs, we assume that they are 50% 1 and 50%. So we take the probability of 0, meaning that the probability that this node is equal to 1 is half. Similarly here and similarly here. Now for the two input NAND, we just mentioned that it's the multiplication of these two numbers. So it's half times half, which is a quarter. Now the inverter, even though we didn't mention it in the table, it's always giving you the complement of the probability. So if you have a quarter at P4, it will be 3/4 at P5 after the inverter. Or basically it's 1 minus a quarter, which is 3/4. Now we know that this is 3/4 at the first input, and here we have a half in the second input. So the probability at the output of the OR, we get it by applying this rule, 1 minus the probability of A bar times the probability of B bar, meaning that it is actually the probability of this one, but it's the complement, which is 1 minus this one, which is a quarter, times the probability of 1 minus a half, which is a half. Now, if you multiply those two together, it will be 1 over 6, sorry, 1 over 8. And then it's 1 over 8. And I mentioned this is actually C, not B. And we calculate P6 by saying that it's 1 minus 1 over 8, which is going to be 7 over 8. And that's the probability of the output of this circuit. We calculate it this way. Notice now we are just practicing finding the switching probability. What we are interested in is the activity factor. Now, how to get the activity factor? We will give you another example. It's this example. We have a 4-input AND, which is built out of 2 levels of gates. These 2 gates is actually 2-level NAND gates. So it's a NAND, NAND, and another NAND. And we were asked to estimate the activity factor at each node if the input have the probability of a half, which is the base case in the beginning of the input. So here we have the probability for each input is equal to half, as we mentioned. So the probability part is going to be half. What we should do, or the easiest way to solve this question, is finding what's in the red boxes first, and then getting the P bar or the associated P bar, and then multiply both of them to get the activity factor at that node. So that's what we will do. So let's find the P first in every line. So in every line, it's actually a half. After the NAND, we know that the NAND, if there's 2 inputs, is 1 minus the multiplication of both properties. So half and half, and you say 1 minus a quarter. So 1 minus quarter is 3/4. So it's 3/4 here, is 3/4 here. At the output is again this circuit here. This is actually an AND, and this is an AND, and this is a NOR. This is NOR circuit. Now the NOR circuits for 2 inputs is actually the probability of A bar times the probability of B bar. Now this one is 3/4 and this is 3/4. So you get the bar. Now we need to calculate it. So the P bar here is a quarter and the P bar here is a quarter. And you multiply them together to get 1 over 60. Now going back, after we calculated what's in the red boxes, go back again to the beginning, find P bar if you didn't find it already. So here is a half. This one we already find it. And this one is 15 over 60. You can see that it's complementing the other probability. So for the activity factor, you multiply both of them. So half and half is a quarter, 3/4 and 1/4 is 3 over 16. 16 times 15 over 16 is actually 15 over 256. And this will be the activity factor of this node. This will be activity factor of this one, the activity factor of this one. And for each one of these nodes, the activity factor is equal. Now we found the activity factor of this design. How to apply this to get the power consumption or the dynamic power consumption. So to do this, or if you were asked what is the dynamic power dissipated in that circuit, which is this one, if the capacitance at the output node of the NAND is 12 femtofarad, so here at the output of the NAND is 12 femtofarad, and at the output of the node is 10 femtofarad, and the system clock frequency is 500 mega and the VDD is 5 volts. So we applied the equation that we now the dynamic power, because we ignored the short circuit power, the dynamic power is the same as the switching power, which is alpha CV squared times F. F is 500. Or we do this for actually each of the output nodes. So here and here and here. You find the activity factor here. You have find the activity factor here and the activity factor here. This will give you the power consumption or the dynamic consumption for this gate. This will give you the dynamic power consumption for this one, and this one will give you the dynamic power consumption for this one. This is the way to calculate the switching power, and then you add all the components. If you have 100 gates, you have to get all of the 100 gates and add them up together. So the switching power for the first NAND is, as we calculated, is 3 over 16. And we found 3 over 16 over here. This is what we get here. It's 3 over 16. 3 over 16. And for this one is 15 over 256. So you just plug it in. This is the activity factor for the first NAND, for the second NAND, and this one for the node. Now, the capacitance associated with the NAND, we said that it's 12 femtofarad. It was given to us. The VDD across the board is 5 squared, or the VDD squared is 5 squared, and the frequency is 500 megahertz. So it's a matter of calculation. You calculate it for the first NAND, it's 28.125 microwatt, and actually you can get it only for the first NAND because they are similar. They are very similar. So you get it for the first one, and you know that the second NAND is the same. For the NOR is calculated to be 7.324 microwatts. So as you can see in this example, we were lucky. So the switching was a lot here, but at the end, and the output was much lower than the first level. So we add those four together, and we end up for this simple gate that, or the conclusion here is that the dynamic power is 63.57 microwatts. Of course, do it for a bigger circuit with so many gates. There are tools that can help you doing this. Now, we will talk about some of the ideas related to the dynamic power, like the clock gate. So one of the best ways to reduce the activity is to turn off the clock to registers in unused block. This requires determining if the blocks are in use or not. If they are not, switch off the clock using the enable gate. So we clock gated. So now the registers, they are actually clock gated by an AND. You can use an AND or any other circuit. Usually we use the AND for gating. So now we have the clock, and we have the registers that saves the value of the enable. Maybe you have an enable logic. If the enable logic is giving you the value of 0, meaning that you will store here in the enable latch 0, and 0 ended with anything. In this turn, it's the clock will give you a 0 that's fed in this clock. So you have a 0 the whole time. There is no clocking going up and down. So since there is no clocking, you don't switch in this register. If you are not switching, you are not having any dynamic power consumption. If you want to enable the circuit, so then you want the enable logic to be 1, and because it's 1 here, then the clock will it will be fed to the register, and it will be clocking normally, but you will consume the power, the dynamic power, to do the job of the registers. Now, this saves the clock activity when alpha is equal to 1. It's eliminating all the switching activity in a block and required determining if the block will be used as we mentioned. Now, for the power and delay trade-off, we mentioned this at the beginning that if you want a fast logic, you must consume a lot of power. So there is a direct relation between them. And this is actually shown here in the equation. So in the equation, if you want fast logic, meaning the frequency is high, then the power switching or the dynamic or the switching power of dynamic power will be also high. So you know that the frequency is actually equals to 1 over time. So it's the reciprocal of the time. So if you want a faster logic, meaning that you want a lower delay, you need to consume more power. That's basically the trade-off between the power and the delay. So reducing the frequency of the supply voltage impacts the delay. Reducing the supply voltage, meaning the reduction in both the static and the dynamic power, but you will slow the logic. Also increasing the V threshold, or the voltage at the source, or Vs, lower the static power, but also slower the logic. So yes, you have reductions in power, but you always have a slower logic. So there is a trade-off between delay and power, as we mentioned, and these methods can be applied to non-critical paths only. So the method, for example, that we explained here, the clock gating, you do it for the non-critical paths. There is another way to do the same thing, which is called the voltage or frequency. So you do this for the voltage frequency, and they call it the dynamic voltage scaling, or DVS, and there is also the dynamic voltage and frequency scaling, so that's the DVFS, and you can see this in many researches. The idea here is to run each clock at the lowest possible voltage and frequency that meets the performance requirements, and we focus on the non-critical paths. We don't want to reduce the frequency of the critical path because it will directly affect the performance. For the non-critical path, we can do the scaling. So in voltage domain, you provide separate supplies for different clocks, and the level converter requires when crossing from low to high VDD domains. The idea here is you have the logic, and usually you need a certain frequency and a certain voltage for this logic to work. Now, if this logic was working and it started to consume more power, you can have some feedback from the core logic, like the workload that you are doing. If it's too much workload, we need to do something about it. If the temperature is exceeding a certain limit, it's getting heated up. So you have these feedbacks to the DVFS controller, where it decides what should be the next frequency and what should be the next voltage. So it gives you a frequency control, and it gives you a voltage control where you have a VDD like 5 volts, and you have a switching voltage regulator where you will have a certain VDD that's maybe it's exactly the 5 volt or lower than that. Maybe 4, maybe 3. It depends on the target that you want. Let's have an example so you understand what's going on. Let's see that this core logic is heated up really badly. So now the temperature is very high. The DVS controller will decide to give you the lowest possible frequency and the lowest possible voltage control. Let's see that here in the voltage and the switching voltage regulator, we have like 3 levels: 5 volts, that's the maximum, 4 volts, and 3 volts. And for the frequency control, in the non-critical paths, you can go from the the maximum frequency, let's call it FM, or 50% of the frequency FM, or 25% of the frequency FM. So these only three levels. Since you are having a terrible temperature, you should have 3 volt here. You should supply the core voltage now by 3 volt and 25% of the maximum frequency of this core logic until it's like cooling down a little bit, and then you can increase it to the second level, maybe give it 50% and 4 volts. And if it's remaining at a certain level, you can increase it to the maximum, go down, and so on. So there is a regulation based on the feedback that comes from the temperature or the workload. Now, this switching voltage regulator works like this. You have a VDD at the high. You have two PMOS connected like this, and you have the X and Y here. And based on the VDD low, the A could be inverted to this P the NMOS here and here. And here you have the ground. Now you have the Y and X here based on the inputs that you have and the A, and you gain at the end those different voltages. And now for the static power. The static power, now we finished with the dynamic power completely. Now we will go to the second major type of the power consumption, which is the static power consumption. The static power consumption is the power consumed while the chip is idle. The chip is idle, it doesn't do any work, but still it's consuming power. This is called the idle power or the standby power consumption. It's usually because of leakage. Leakage stores power for the nominal off devices. So they are off, but still they are leaking some current, and this current will be in turns will be converted to power, where you will consume power whether you are working or not. In this case, you are having off devices. Now, ratio circuits burn power in a fight between the on transistor. Now, what are the sources of this static power consumption, or where did the leakage happen? It happens in the subthreshold leakage, the gate leakage, and the p-n junction leakage, and also the contention current. The contention current, we ignore it. We will also ignore the p-n junction leakage. We will only focus on those two. The subthreshold leakage, as you can see, you'll have a current going this direction in the channel. The gate leakage will have a current going to this direction, and notice that in the gate there's not supposed to be any current going from gate to the rest of the remaining body of the transistor. But we have a leakage. Similarly, we have the junction leakage, where the direction is the opposite of the normal p-n junction. So we have a leakage. Now the static power consumption is approaching 30% to 40% below the nanometer generation or feature size. We need to understand the sources of these leakage to reduce the static power consumption. But this is actually an advanced for the advanced course. Since this is an introduction to VLSI design course, we will just focus on how to calculate the subthreshold leakage and the gate leakage. So let's revisit our example, the one that we have 1 billion transistor broken down to 50 million and 950 million for the logic and the memory respectively. So we want to estimate the static power consumption. It was given to you that the subthreshold leakage, if you have a normal V threshold, it's 100 nanoampere per micrometer. If you have a high V threshold, it's 10 nanoampere per micrometer. And remember that the power actually for the static power consumption is the one that you already know. The power is equal to the current times the voltage. Now, we know that there are leakages in the current. The voltage is usually the VDD, which is maybe in this example, the voltage that we give it to in the previous example, when we talked about the dynamic power, we said that the voltage is equal to 1 volt. So it's 1 volt. That's it. The voltage is there. It's constant. It's remaining there forever. It's 1 volt. But the current, it's changing based on the situation. So in the sub-threshold leakage, we have broke it down into two parts, the normal V threshold and the high V threshold. So if you have a high V threshold, which is this one, you will have a low current, which is 10 nanoampere per micrometer. If you have the normal V threshold, which is actually less than the high V threshold, then you will have higher sub-threshold leakage. So you can see the relation here. Now, it was given to you that the normal V threshold, as we said, 100 nanoampere per micrometer, and for the high V threshold is 10 nanoampere per micrometer. Also, the high V threshold, it's not all the time. It's used in all the memories and 95% of the logic. So basically, most, except a little bit, which is only 5% of the logic gates where you use normal V threshold. Now for the gate leakage, it's 5 nanoampere per micrometer across the board. For the junction leakage, we neglect, so it's negligible. So we will make an assumption. This is actually a very important assumption that you need to understand, that we will assume that half the transistor have leakage and half the transistor doesn't have leakage, meaning that sub-threshold leakage and also the gate leakage, both of them. Why we are making this assumption? Because we don't know how the transistors are leaking. We have billion transistors. So some of these billion transistors will have like high leakage, some of them will have low leakage because of the process variation. So to be fair, this is the assumption that we are making, that half the transistor will have the leakage as we specified, and half of them have no leakage because of this process variation. So to solve this question, we said that the normal V threshold have 5% for the logic and 95% is high V threshold. For the memory, all of them have high V threshold. Again, we have the current given to us in all of them in terms of nanoampere per micrometer. So we need to find how many micrometers we have. And then we multiply by the current to get the current in terms of ampere. So we will get the width in the normal V threshold and in the high V threshold, because we are breaking it down this way. So in the normal V threshold, we have 5% of the logic. So we will multiply 5 billion by 5% times the 12 lambda it was given to you when that example, when we talked about the dynamic power. So it's time 12 lambda times 0.025 micrometer per lambda. Now the lambda will go with the lambda, and you will end up with 0.75 times the 10 to the power of 6 micrometer. Leave it this way. I know you can cross this and this, but leave it this way so we can get the power easy. So we leave it this way. It's 0.75 times 10 to the power of 6 micrometer. Now for the width in the high V threshold, now we have two situations, the 5% and the 95%. Sorry, the 95% and the 100%. So we have 90% for the logic. So that's 50 times 10 to the power of 6 times 95% times 12 times 0.05. For the 950, which is the memory, it's 950 times 10 to the power of 6 times a 100, because they are 100% high V threshold, times 4 lambda times 0.025. And from this calculation, after adding those two, we get 109.25 times 10 to the power of 6 micrometer. You can compare both of them. If you add them together, the sizes, both of them. So the width will be 110. But since we have the breakdown, we'll have it like this, because we have different leakage for each one of them. For the sub-threshold leakage, we will calculate it this way. We will take the normal V threshold and the high V threshold. So this number and this number. this number, it will be multiplied because this will be the 100 nanoampere per micrometer, which is the one that we mentioned here. It's for the normal V threshold. So the 100 for the normal V threshold. So we will go here and we will multiply the width of the normal V threshold, which is this one, by the 100 nanoampere time divided by, or nanoampere per micrometer divided by 2. Notice that for all these calculations for the subthreshold and the gate for the current, the subthreshold current and the gate current, all of these calculation is actually divided by 2 for the assumption that we just made, which is this assumption that half the transistor have. This is why we divide by 2. So if we made this assumption, then we will multiply those together plus the other one, which is the high V threshold, times the low current, which is 10 nanoampere per micrometer. If you calculate this, it's going to be 548, sorry, 584 milliampere. So that's what we will have for the subthreshold current. Now for the gate current, we do the same, but now we have only one current, which is 5 nanoampere per micrometer. If the question gave you different currents, sometimes he give you a current if you have a thin gate oxide and another current if you have a thick gate oxide. So if you have a different breakdown, you will multiply by the corresponding current. Here we have 5 nanoampere divided by micrometer for both of them. You divide it by 2 also to get the result, which is 275 milliampere. Now notice, because we kept the 10 to the power 6 times microampere, because we kept the micrometer, we could cross it with this one. Simply cross it with this one, and we calculate. Since you have 10 to the power of 6 and you have nano, which is 10 to the power of minus 9, you get the result in milliampere. Similarly, now for the static power consumption, you calculated the current. So you add the current or the leakage current from all sources, which is from the subthreshold and the gate in this example, because we neglected the junction leakage. We multiply those two, we add this and this, and we multiply it by 1 volt, and the result will be 859 milliwatts, which is approaching 1 watt. 1 watt. And you can see that we used actually an old generation. Because of this, the static power consumption compared to the dynamic, the static is about 1 volt, oh sorry, 1 watt, and the dynamic we calculate to be about 6 watt. So you can see that the dynamic gives you more power consumption more than the static. But with newer versions, with newer generations, when we have smaller transistor, the leaking is increasing rapidly, to the point that now the static power consumption is actually the dominant part. The static power consumption is the dominant part in recent technologies. Now for the junction leakage, we neglect the junction leakage. It's actually because from the reverse bias being junction between the diffusion of the substrate, ordinary diode leakage is also negligible, as we mentioned. There's 2 sources, one from band-to-band tunneling, the BT-BT, which can be a little bit significant, especially if you have high V threshold. Also, there is a gate-induced drain leakage, the GIDL, which excess rebates or getting worsened when the V from the ground to the diffusion is minus 3dD or more negative. When this happens, then it's getting worse. We are keeping this in check because we are ignoring it. Maybe if in recent generations, this will cause terrible leakage that we need to take account for. Now, how to reduce the static power consumption? Remember, we had the clock gating in the dynamic power. In the static power, we have the power gating, meaning we turn off the power to blocks when they are idle to save leakage. We use virtual VDD or VDD-V, which is this one. And the gate output, we might make this the gate outputs to prevent the invalid logic level to the next block. The voltage drop across sleeve transistor degrades the performance during the normal operation. So we size the transistor wide enough to minimize the impact, and the switching wide sleeve transistor costs dynamic power only justified when the circuit sleeves long enough. So we have a sleeve and we have idle, we have normal operation and so on. So the idea here is if you have a power gated block, we have a block. Normally we give it a voltage VDD and the ground, and we give it the input, and we are waiting for the output send before we do the power gating. Now to do the power gating, we plug in this block, which is PMOSes in parallel. It works when the sleeve is equal to 0. So when the sleeve is 0, you have 0, 0, 0, 0. So this is 1, this is 1, this is 1, and this is also 1. So the VDD will become in the VDD threshold. And here the output will be if you have sleep is equal to 0, meaning that you are not sleeping. So if you are not sleeping, this will be 1 and 1, and you will have the normal output. So in normal operation, you will have a VDD and the output will be generated to you. Now, if you don't care about this block and you don't want its output, what will happen? This will be completely closed, meaning it will be off, 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 and off. All of them will be off. So you don't have a VDD here. You don't have a VDD here. And this will happen if you have sleeve equal to 1. If sleeve is equal to 1, all of them will be off. There is no VDD powering the block. So it doesn't work. It doesn't consume static power. Not only this, we prevent the output of the block to be generated in the outer output. So if your sleep is equal to 1, meaning that the sleep bar is equal to 0, since it is 0, you are zeroing out all the outputs. So by plugging these two plugs, if you don't care about this gate or certain block, you don't want it to work, you block it from the output, and you also don't give it any VDD. And this is what we mean by the power gate. Now, this time we finish the power consumption, and next time we will talk about the main memory, especially the SRAM, and after that we will see the testability.